Good morning to you all. Can you hear me?
Yes, madam. Good morning.
Yes, madam.
There is only 119 students. Did the message pass correctly? I guess there are more students to come. Do you have any lecture before 10:30? I guess no. Right. Okay. So actually, I was about to take the tomorrow's lecture, tomorrow's time slot in 10:30 and 10:30 to 12:30. But Professor Darshana wanted that slot, so therefore I took this session. So actually I want to finish the syllabus as early as possible because I'm about to take leave again. So next Thursday as well, you have the stat lecture, right? So keep in mind that next Thursday also you have the lecture. Not only the lecture, actually, there will be a quiz, right? I'll preparing a quiz for you in next Thursday, 10:30 to 12:30. Actually, it's not all the 2 hours, but probably 1.5 hours. So MCQ questions. So be prepared to that as well. So the questions will be based on the things what we have done up to so far, right? Including what I'm going to do today as well, right? So before conducting the quiz, I hope to discuss all the questions and the problem sheets I gave you. So, so be well prepared on the first quiz, right? It's on next Thursday. Okay, the date is 9th, right?
Madam,
9th of December.
Madam, at this time we have a IMGT tutorial session.
I mean Thursday. Thursday is allocated for the maths department, isn't it?
Yes, madam, but Amanda ma'am is not December 3 tutorial and she select that date.
But that time slot is allocated for our department, Puta. So I'll discuss with her and also with the department head, and I'll inform you. So according to your timetable, as I remember, that time slot is allocated to our department, right? So I'll talk with her and also with the head of the department, and then do something, right? So definitely there is a quiz next week, either Wednesday or Thursday, right? Then yes, did she tell that every Thursday she is going to take that spot?
No, madam.
Only for next Thursday?
Oh, yes.
Or this Thursday, tomorrow one?
December 9, ma'am.
9th of December.
Yes, ma'am.
Right. Okay, I'll talk with her and inform you, but most probably the Thursday time slot will be taken by me, right? So I'll ask her, right? Okay. So be prepared for the quiz. Somehow next week you have either Wednesday or Thursday. I'll inform the correct date. Go through the LMS regularly, right? It's better. So I can pass a message through LMS. So it's better to be updated. So please visit your LMS of my course regularly. Okay. Right. What are the other things I have to Yeah, that's all. Any problem? Do you have any problem regarding the quiz? It will be a MCQ one, right? It's not a tough one since it's your first quiz, and also first chapter also you are familiar with. So it's just a simple quiz, right? So don't hesitate. Study well. Go through your notes. Okay, right. And also another thing, today you will hear another voice rather than me, right? It's my kid, so just ignore that voice and be concentrate on my voice, right? Okay. So up to now, we discussed. Actually, we are under chapter 2 now. Under the chapter 1, we discussed some basic concepts on probability. What you have learned in A-level class, right? What is an experiment, event, sample space, and probability rules, Bayes rule, conditional probability, likewise so many basic things under the probability. And in the second chapter, we learned what is a random variable, right? Random variable under the random variable, discrete and continuous random variable. What is a discrete random variable and what is a continuous random variable? And then about the distribution functions, probability distributions, simple fx. So probability distribution under the discrete random variable, it is called probability function or the mass function. And under the continuous variable, it is the density function, right? Then the cumulative function also we learned, right? Then the next thing we learned is expected values. So we learn how to obtain expected values, and using the expected values, how to obtain the variance as well. Okay, so those are the things we discussed so far. So today I'm going to discuss about moments, right? Okay. Did you download the material? This is part 3 of the chapter 2. So moments, right? Moments in statistics are popularly used to describe the characteristic of a distribution. It is a quantity that expresses the average or expected value in the first, second, third, or fourth power of the deviation of each component of frequency distribution from a given value, typically mean or zero. So moment are used to describe the characteristic of a distribution, right? So as I said earlier, can you remember that there are two most important properties in a function, distribution function, that is mean and variance, right? Moment is also like that. Those two are also included in the moments. So we can calculate first moment, second moment, third moment, fourth moment, and so on, right? So the moments are quantity that express the average or expected value. Average or expected value of the first, second, third, or fourth power of the deviation. Right? Can you remember when we find the median, first quartile ranges, quartiles, first quartile, second quartile, third quartile, and interquartile ranges, It also describes the distribution, the dispersion of the distribution, like that like that quartiles. Here the moment express average or expected value of first, second, third or fourth and so on, power of the deviation, right? Power of the deviation means the first power is x, second power is x squared, third is x third cube, x fourth, and so on, right? So if we just take the expected value of them, those are called, this is first moment, and this is the second, this is the third, and this is the fourth, right? If we take the expected value of those things, right? So those are called the moments. It describes the characteristic of the distribution. Using the first moment, it describes the mean. Using the second moment, it describes the variance. And using the third moment, skewness, and the fourth moment, kurtosis, right? Skewness, kurtosis, can you remember those words? Skewness, skewness කියන්නේ සිංහලෙන් ධන ව්‍යාප්තියක් ඍණ ව්‍යාප්තියක් කියලා ඉගෙන ගත්තා මතකද ඒ ලෙවල් වලට? මතක නැහැ සිංහල වචන. Skewness, negative skewness and positive skewness. If a distribution is like this, the tail is to the right, so it is a right skewed. And if it is like this, it is a positive, left skewed or negative skewed, right? Left or negative, right or positive, this one, skewness, right? And kurtosis, right? So using the first moment, it obtained mean, and the second moment, the variance, and the third moment, skewness, and the fourth moment, kurtosis. Likewise, you can obtain any power of deviation, right? So that is called moment. So moment describes the characteristic of a distribution. So any distribution, there is a characteristic, mean, variance, skewness, and kurtosis. So using the characteristics, we can identify the distribution. So in the next chapters, we are going to learn the distribution types, right? There are so many distributions, and using the properties of distribution, we can identify what is the distribution is. Okay. Okay. So moments are simply the mathematical expectations defined earlier, right? So moments, there are two types of moments. Moment about the origin, about the origin, and moment about the mean, right? So here I said that power of the deviation of each component of frequency distribution from given value typically mean of zero. Deviation, we take either mean, deviation from mean or deviation from zero, right? If the deviation is about zero, then it is called moment about the origin. And if the deviation is calculated about the mean, it is called rth moment about the mean, right? So first one is rth moment about the origin, that is the deviation measured around the 0. This is the expected value of xr and given by, so it is noted as mu r dash or mu r prime. So it is the expected value of the rth power of x, or x to the power r, rth power of x. It's just the expected value of x to the power r, right? So in discrete case, we can write it as summation of all x xr fx, right? So this is how we find rth moment about the origin. Okay. So what happens when r is 0? When r is equals to 0, it's just the summation of x. Sorry, it's just the summation of fx. So for all x, the summation of fx. So it is summation of all x fx. So you know that is equals to 1 for all x. So it is 1, right? So what happens when r equals 1? When r equals 1, here r becomes 1. So it's summation of x fx. So we know that the summation of x fx is the expected value of x. So that is mu1 dash. So it is the mean of the distribution, as I said earlier. Using the expected value of x, we found mean, right? So the first moment about the origin is the mean. Okay. So that is the moment about the origin. Then what is moment about the mean? The rth moment about the mean. So as I said earlier, it is the deviation from mean, right? It is the deviation from mean. Rth moment about the mean defines to the deviation from the mean. So this is expected value of x minus mu, deviation from mean, right? So it's not just x, it's x minus mu now, right? It's x minus mu. Right? So the rth moment about the mean is denoted as mu r. So the moment about the origin is denoted as mu r dash or mu r prime. Moment about the mean, just mu r, right? So it is the expected value of x to the power r, right? But here it should be the simple x minus mu to the powers r, right? Here it should be r, correct it as r. It should be r here, not 2. Okay. So for the discrete case, we can write it as x minus mu to the power r to fx. Okay. So this is the rth moment about the mean. So what happens when r equals 0? Again, when r equals 0, it's just the summation of all x fx. So it is equals to 1. And when r is equals 1, it is x minus mu into fx. Right? So it becomes 0. How? Right? So it becomes x, yes, x minus mu fx. Then it becomes, yes, here, like this, right? So it's just summation of x minus mu into fx. So it can be written as summation of x fx minus mu into summation of fx. So we know that summation of fx is equals 1. Okay. Then summation of xfx means the mu. So here mu into 1 is mu, that is equals to 0. That's how it becomes 0. Right? Then when r is equals to 2, mu 2 is expected value of x minus mu square. So if you can remember, this is the variance sigma squared of the distribution, the random variable x. Right? So the first moment about the origin. Oh, yeah, it's a mistake again, I guess. Right, no, this is not right. Okay. So the first moment about the origin is the expected value, and the second moment about the mean is the variance. About the mean is the variance, right? Not about the origin. Second moment about the mean is the variance, right? So that is how moment works. Okay, moments are just the expected values, but the power of the random variables. Okay, so there are two types of moments: moment about the mean and moment about the origin. It just depends how you take the deviation. If the deviation is about the mean, it is the moment about the mean. If the deviation you take around the 0, then it is the moment about the origin, right? So any question, any problem up to now? Okay, I guess no then, right? Okay, so when the order is higher, right? 5, 6, 7, 8, there, if the order is higher, the deviation is higher, power is higher, so it is difficult to calculate just using the expected values. So rather than doing that, we use a function called moment generating function. Moment generating function. So as its name hints, moment generating function is literally the function that generates the moments. So using this moment generating function, we can easily calculate the moments, right? So the moment generating function, there are two types for discrete case and continuous case. So the moment generating function denoted by mxt, and it is the expected value of e to the power tx. So that is the definition, right? So the moment generating function is the expected value of e to the power tx, right? So expected value of any value can be written as summation of In the discrete case, summation of that, the thing within the brackets of expected value and the fx, right? So for the discrete case, it's a summation e to the power tx into fx, and for the continuous case, it is e to the power tx to the fx dx, right? So now I'm going to discuss how we can obtain moments using the moment generating function, right? So Ex, we can write Ex using the Taylor series like this. 1 plus x squared to the factorial 2 plus x3, x cubed over factorial 3, likewise xn over factorial n, right? So this is the expansion of Taylor series. We can write Ex like this. Okay, then this is Ex, and we can write e to the power tx, just in place of x, substitute tx. So it becomes 1 plus tx, t squared x squared over 2 factorial 2, and t cube x cube over factorial 3 up to tn xn factorial n, right? So now we are going to take the expected values. Okay, expected values. So expected value of e to the power tx, just take the expectation, right? So if we expand it, so we can write it as expected value of 1, t into expected value of x, t squared over factorial 2e expected value x squared, likewise up to tn over factorial n into expected value of xn. Then we are going to take the derivative with respect to t. We are going to obtain the derivative of the expected value of etx with respect to t. So dt e1, then yes, the whole thing, oh, sorry, right. So now we are going to take the derivative, right? So d over dt e1, so it's just 0, right? Then t if we take d, oops, okay, can you see the screen now?
Yes, madam.
Okay. Then if we take the derivative t into ex, it's just ex, right? So here it's 0 here, and here it becomes expected value of x. This becomes ex and t squared over factorial 2 e to expected value of x squared. If we take derivative with respect to t, it is 2t over factorial 2. So it's just t into expected value of x squared, right? Then plus the next one, t cube over factorial 3 expected value of x cube. If we take the derivative with respect to t, then it becomes 3t squared over factorial 3. So it becomes t squared over 2 expected value of x cube. So likewise, when it comes to tn, there should be a t term there, right? So if we plug t equals 0 there, so this is already 0, and ex, here if we plug t equals 0, it becomes 0. If we plug t equals 0 here, it also becomes 0. Then up to n, all the values are 0 since t is 0. So the first derivative is equals to expected value of x, right? Okay, if we take another derivative, then what happens? What we get? So again, this becomes 0. This becomes 0 if we take another derivative. That means for the original one twice, right? If we take derivative here, now it becomes expected value of x squared. Here it becomes 2t over 2, that is t into expected value of x cube, right? So if we plug t equals 0 to the second derivative, the remaining part is expected value of x squared. Okay. So if you take another derivative, therefore total twice, you will get expected value of x squared. So if we want to find expected value of x to the power r, so take the derivative of moment generating function r times and plug t equal 0, right? So then you can obtain the moment corresponding to the random variable, right? Is that clear now? So what you have to do is find the expected value of the x to the power r, that is rth moment. You have to take the derivative of moment generating function r times and plug t equals 0 in. So this is the equation. Right? Obtain the derivative r times dr over dtr, mxt is the moment generating function, then plug t equals 0 in. Right? So if we want, earlier we proved that if we want the expected value of x, then derivate the moment generating function expected value of e to the power tx with respect to t once Once here, this is 1, right? R is equals to 1. Then plug it, T equals 0. Then you can obtain Ex. Likewise, if you want the rth moment, just obtain the moment generating function and obtain the derivative with respect to r and plug T equals 0. Right? So in earlier case, we took the summation and integrals to find moments. Can you remember the moments? How we found the first moment? If the case is continuous, integral all x. If it is the first moment or the say rth moment, xr fx px. There, to find the rth moment, we took the integrals, but using the moment generating function, we can take the derivatives rather than doing integrals and find the moments. What we have to do is find the moment generating function first and then derivate it with respect to the deviation you want, with the moment you want, and then plug T equals 0. Right? I think now it's clear. Okay. Any question? Okay. Then the example, find the moment generating function of the following distribution. So actually this is an exponential distribution. So in next chapters you are going to learn some special functions. So this is also a special function called exponential distribution, right? Fx lambda e into minus lambda x if x greater than 0 or 0 else, right? So now we are going to find the moment generating function. So moment generating function is denoted by mxt. So it is the expected value of e to the power tx. So using the integration, we can write 0 to infinity e to the power tx lambda e to the power lambda x dx. So here the lambda is a constant, right? Here the lambda is a constant. So we can take lambda out and the integrals of e to the power t minus lambda to x dx. So if we obtain the integrals, it can be written as 1 over t minus lambda into e to the power t minus lambda into x. And the limits are 0 to infinity. So it becomes lambda over lambda minus t. Right? If we substitute infinity to x, e to the power infinity, it close to 0. Sorry, 1, I guess, 1. Yes. So the moment generating function for this distribution is lambda over lambda minus t. Okay, so this is the moment generating function, right? So now if we want to find moments of this distribution, you can just obtain the derivatives, right? So using the moment generating function, if you find the third moment, for an example, say we want to find the third moment. If we use moment generating function, this is how we're going to use it. d3 over dt3 of cube lambda over lambda minus t, right? This is the way how we obtain the third moment using the moment generating function. If we calculate it just by using integrals, the expected value of x cube, it is from 0 to infinity x cubed over lambda e to the power minus lambda x dx. So there are two ways to find. We can just, by the definition, if we want to find the third moment, we can use expected values of x cubed over x cubed into the function and integrate it. Or else we can use the moment generating function. So which one is the easier to calculate? This integral or this one? So it's very easy to calculate using the moment generating function rather than using this integral. So that's why we are using moment generating function. Right? From any way you can find the moments, but using moment generating function, it is easy to calculate moments. Right? Okay. Any questions?
Madam,
Yes.
madam, I don't get the mxt one. Isn't e to the power infinity is infinity?
No, it's 0.
I know e to the power 0 is 1. E to the power infinity is 0.
Sorry. Yes. It's 1. Then,
Yeah.
then lambda.
Okay.
Lambda into 1 over t to lambda. Then e to the power infinity is 1. So it then minus, if we substitute the value of 0, E0 is 0.
Okay.
So it
Thank
becomes
you, madam.
lambda over t minus lambda, right?
Okay. Understood, madam. Thank you, madam.
Just substitute the values of the integration after the integration, right? So you get lambda over lambda minus t. Clear now?
Yes, madam.
Okay. Okay, that is how moment works, right? So we can use either the definition to find moments or the moment generating function to find the moments. Okay, so moments are important to describe the characteristic of a distribution, right? Okay. Okay, now take a 5 minutes break, right? Take a 5 minutes break. I'll come around 11:25. Okay. Okay. So someone has asked me to conduct the quiz in this time slot. That means Wednesday 10:30, 12:30. Are you all free on that time? But the problem is that this time is allocated to the Department of Industrial Management, right? In according to a timetable. So today I got this after discussing with Professor Darshana because he wanted a tomorrow slot 10:30 to 12:30. So I'll discuss and inform you, right? Okay. Can you hear me?
Yes, ma'am.
Yes, madam.
Okay. Now next, as the last topic, I'm going to discuss here another way of obtaining probability using the density function, right? So using the density function, we know that the regular method is to obtain the integral over the x or the given range, right? But rather than using that, we can use the graphical way as well, right? A continuous random variable x is specified by its probability density function, which is written fx, where fx is greater than or equal 0, throughout the range of values for which x is valid. This probability density function, we are just called PDF, can be represented by a curve, and probabilities are given by the area under the curve. So we can represent the fx graphically, since we know the values of x, and using the function we can find the values of fx. Then we can draw a curve or a graphical representation to denote the probability density function PDF. Then we can calculate probabilities using the area under the curve. The area of the probability density function represent the probabilities, relevant probabilities, right? So here, let's discuss an example. X is a random variable. The delay in hours of flight from airport A, where fx equals to 0.2 minus 0.02x. Here, x is in between 0 and 10. So this is the probability density function, or the PDF. So we have to answer two questions. Find the probability that the delay will be less than 4 hours, and the probability that the delay will be between 2 and 6. So using the definition of PDF, how we can obtain this? The first one, so if I use the space given here, I just use in this space, right? So we want to find probability of the delay will be less than 4 hours. So it's the probability between 0 and 4. The delay less than 4. So we can find it if we take the integrals from 0 to 4, the function fx right? So it is 0.2x minus 0.02 x squared over 2, substitute values 0 and 4. So it is 0.8 minus 0.16. The answer is 0.64. Okay. So this is how we find it in usual way. If it is the integral of fx dx. Okay. But we can use, instead of this, we can use the graphical representation, right? Since fx holds 0 to 10, the delay can be between 0 and 10 hours only. So x is from 0 to 10. We first draw a sketch of fx, right? So x values are in between 0 and 10. Then for x-axis we take x, and for y-axis we take the function fx, right? So we can draw a line here. Okay, when x is 0, we know the value is, when x is 0, this part becomes 0, so it's 0.2. So here the value is 0.2. Right? So this is the sketch. Okay. Now we want to find delay will be less than 4. So 4 is somewhere here. Okay. So this area gives us the probability values. If we denote x using x-axis and the function fx using fx, then the area under the curve will give you the probability values. Okay. So if we want the probability that the delay will be less than 4, if 4 lies here, then this area will give you the delay will be less than 4. So how you find this area? How you find this area? So this is a trapezoid or a trapezium. How you find it? So you know the x here. So you can find what is the value here. Okay, using the fx, just by substituting 4 into fx. If this becomes 4, then it is 0.2 minus 0.08. Right? So it is 0. Here it is 0.12. So now how you find the area? Find it. How you find it? You have to just add the two parallel lines and divided it by 2 and multiply by the perpendicular line or height. Right? Rushi, no, it's not. Yeah, others are correct. Tarushi, you are not correct. See the calculations again. Yes, 0.64. So that is the probability we found earlier. Can you remember it? So the area under the curve of the fx gives us the probability. So it is another way to find probability values. Okay, now go to the next part, part B. The probability that the delay will be between 2 and 6 hours. Send me the answers. Praveen. So it's already 4 weeks has gone. So how's your university life? online teaching is good though? Do you need to come physically? Which one you prefer?
Yes, madam, we like to come physically.
Want to come physically?
Yes.
ඇත්තටම මේක ඉතින් යුනිවර්සිටි ලයිෆ් එකක් නෙවෙයි නේද? අපි ඉතින් අපි යුනිවර්සිටි යන කාලේ වෙනස් ඉතින් මේ එක්ස්පීරියන්ස් එක වෙනස්. යුනිවර්සිටි කියන ෆීලිං එක එන්නේ නැහැ නේද? Right. So most of your answers are correct, right? So if you sorry. I'm sorry. Okay, the probability that the delay will be between 2 and 6 hours. So we need to find so it is the integration of 2 to 6, 0.2 minus 0.02 x into dx. It's 0.48, right? So if we use the area under the curve, so it is in between 2 and 6, right? And if we substitute the 2 here, it is 0.2 into 2, it is 0.1, 2, yes, 0.16 here. If we substitute 6, 0.12, 0.08. So it's just 0.16, this area, right? I have to find this area, 0.16 plus 0.08, the two parallel lines, divided by 2 by this height, 4. So it becomes 6 and 8, 24, 0.48. Okay. So the total area under the curve gives the total probability. So it must be 1, right? So we know that the total probability of a function should be equals to 1. So we can check it if we substitute the values. So we know that if we take the integrals over the range, it should 1 as required, right? So for all x, that means to minus infinity to plus infinity. But according to this problem, the delay can be take within the range 0.10. That's why we are substituting 0 to 10, by not substituting minus infinity to plus infinity, right? According to the question, the range is changing. So it's 1, we know it, we already knew it. And according to this example, if we find the area, so it is area is, so this is a triangle. So area under the curve is half into 10 into 0.2. So it is 1. So now it's clear that the area under the curve gives us the probability. Okay. So actually it's possible. Is it possible to find the delay in say 3 hours, exactly 3 hours? Actually, it can't find. We can only find probability that x lies within a particular range here, right? In density function, using the density function, we can only find the probability that x lies within a particular range. So it's not possible to distinguish between p x less than or equal to 2 and greater than or equal to 2 or greater than 2, or likewise there is no any difference, right? We can't find the exact probability of exact point. So there is no need to worry about whether the equality is strict or not. Okay. So any questions up to now? Okay. If you have any question, you can ask now. You have the time. So today 3:30, 5:30 time slot will be taken by the tutor and discuss the tutorial number 1 and 2. Right? Then I have to discuss problem sheets, right? So next week, I will upload the answers to the problem sheets to the LMS, and I'll give you time to ask whether there is any problem in that problem sheets, right? Any doubtful things, you can ask me. So I'll upload the answers to the problem sheets next week, by next week. Next week means before Monday, right? Before Monday, I'll upload. Then you have time to study. So there may be 30 to 40 questions for the MCQs, and the allocated time will be 1.5 hours. So you have to be within that time period. So if you have any problem, inform me earlier. Okay. Then I can give you a solution if you inform me earlier. Okay. Any questions? So then this is the end of chapter 2. So after that, we have to move to the chapter 3 and 4, the special distribution functions. There are so many distributions under the discrete case and the continuous case. Those are very important things, because in next levels, in level 2, level 3, level 4, if you are going to be with statistics, then you should know all those probability distribution functions, right? So it's very important to be in the lecture, or else right? You can learn it from somewhere else, but somehow you have to learn. Okay, so it's very important in statistics to learn the basic things. So let's find out here now. Yes. Okay. Right. So participate today's tutorial class. She will be send you a link, right? Okay. Yes. Thank you.
Thank you,
Thank
madam.
you, madam.
Thank 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 you.
You're welcome.
Yeah.
Okay.